All right, so yesterday we left off on the inequalities, and we said sometimes it's easier to graph them. Like for B and C, it's easier to see the solution if you graph them. But if it's a linear inequality, then you can just straight up solve them. There's no tricky thing about it. The only thing to watch out for is that if you're multiplying or dividing by a negative number, then you have to flip the inequality. All right, so now let's look at these new questions. And again, the tools we needed to attack these problems, we already have it. It's basically finding the derivative. But now the algebra is going to get a little bit more tricky because you're not going to be having just x by itself. Like in this question, we have a rational function. Not that difficult, but also not that easy. Now it says find the second derivative. So let's just talk about notations. F prime of x means you're finding the rate of change, the slope, whatever. But this prime, you only have one symbol there. This is called the first derivative. You can have something like this, f prime of x. This is called the second derivative. You can have f triple prime of x, which would be the third derivative, yada yada. So a quick example of this, let's say you have x to the power of 4. Let's say this is y. What will be y prime? What would be the derivative of x power 4?
4x cubed.
4x cubed. What will be y double prime? Means the derivative of this.
12x squared.
Yeah, so that's the idea. So you can keep going until you get a 0. So 24x, y quadruple prime would be 24. And the derivative of a number, I guess, this is just going to be y, 5 lines. I'm going to call it yv. This is going to be 0. So any polynomial that you start off with, the final derivative will always be 0. Only for polynomials, though. Only for polynomials. Let's try another example. Let's say square root of x, which is x power 1 over 2. You will see that this one, it never stops. It'll never be 0. This can go on forever and ever and ever. Y prime will be 1 over 2 root x. Y double prime will be 1 over 2 times negative 1 over 2 times x to the power negative 3 over 2. Y triple prime will be, well, now this comes down, so negative 1 over 4 times negative 3 over 2 times x to the negative 5 over 2. As you can imagine, this is going to go on forever. It's only polynomials, and remember what a polynomial is. This power has to be a whole number greater than or equal to 0. If it's 1 over 2, nope. Negative 1 over 2, nope. 3 pi, nope, not a whole number. Has to be a whole number, has to be greater than 0. Those are polynomials, they always stop. But non-polynomials, nope, infinitely. There's an infinite number of derivatives. So anyways, let's look at this rational function. You have something over something, it's a rational function. We will find the derivative of this. How should we do this? So this is f, this is g. Remember, this is a quotient rule problem. It's going to be f prime g minus fg prime all over g squared. So what's f prime of x?
It's 1.
So we have to do it, right? So f prime is 1, and g by itself is 1 plus x. So you can just write that as 1 plus x. Minus f is x times g prime. What's g prime?
It's 1.
It's 1, so just that. All over g squared, so 1 plus x squared. This cancels out with this, right? So now we have 1 over 1 plus x squared. If I move this up, what does that become? What's the new power?
Negative 1.
Negative 2, because there's a 2 with it. Because we squared the g. Remember, in the quotient rule, the g is squared. So this is f prime of x. Now we can take this a level deeper. What will be f double prime of x?
You bring the negative 2 in the front.
So it'll be -2, 1 plus x, new power is -3. What do we multiply this
By 1.
by? 1. Boom. That's the final answer. If you want to clean this up, it'll look like this. -2 over 1 plus 3 cubed. Final answer for the double derivative. So it's not too hard. You just need to do it again. That's the entire thing. Now let's talk about something else. Where's derivative very widely used? It's used in physics. Well, it's used in everything, but this book kind of goes into it from a physics perspective. So in physics, you have three different things. You have displacement, which means it's a vector quantity, and the scalar equivalent is distance. So what's the difference between these two here? Let me show you. Let's say this is O. You go to some point A, that's 5 kilometers, and then you come to some point B, which is 5 kilometers, and let's say this. How do we find this distance from here to here? Yeah, good question. We can't. We need to specify that angle. Let's say it's some angle there. Let's say this distance is 7. That takes you straight from O to B. So what's the total distance traveled by this individual? The total distance, well, we just follow the path. The distance is path-based. So what's the total distance traveled by this individual from here to here to here?
17.
So he doesn't come back. He just stops here. Goes from O to B. So we're going from O to B. So the distance
So
would be
7.
10. Sorry, you're right. It'll be 7, but we're talking about distance, okay? So when we're talking about distance, we need to think of it as the path that the person took. So the person could have gone here, but he didn't. He went from O to A and A to B, right?
Mm-hmm.
So the scalar distance the individual traveled is 10 kilometers, 10 units, whatever. Displacement is the shortest possible distance. So what's the shortest possible distance between those 2 points?
7.
7. So that's the difference between a displacement and a scalar. Displacement is a vector quantity, which means it requires a magnitude and it also requires a direction. So we're going to say 7 north. Distance doesn't. So that's the highest level. That's on the top. A level deeper, we have velocity. On this end, on the other end, we have speed. Both of these are slopes, okay? Both of these are slopes of distance versus time graph. So for speed, again, we need a time. Let's say this is 5 seconds. So the formula for speed is distance over time. So this individual traveled 10 kilometers in 5 minutes, hours, whatever. The speed is 2. Velocity is displacement over time. So this individual traveled 7 kilometers, let's say in 5, whatever. It's going to be 1.4 and then north. So that's the difference between velocity and speed. You can get this. They're literally the rate of changes from these two. And then the third level, there's no speed equivalent. There's no scalar equivalent for this. This is acceleration, which is the slope of velocity versus time graph. Again, this is a vector quantity. So what do all of these mean? Okay, let's do an example. So I think it's important to understand what's going on. Sometimes it's also called position. versus time. Instead of distance versus time, it's called position versus time as well. So let's say there's some individual that went from the origin to some point A. This is 5. Let's say this is 50. Let's say this is hours. Let's say this is kilometers. Remember, this is distance or position. What is the slope of this line?
It's 2.
It's rise over run, so I don't think it's 2, it's 10, right? 50 over 5, it's 10.
Mm-hmm.
It's 10. So now look at this. Velocity, right? Velocity is the slope of the distance versus time curve. So the slope here is constant. We start here, we go to 5. The slope is consistently 10. So the velocity of this individual was 10 kilometers per hour. We need this angle. Let's say it's 38 degrees. 10 kilometers per hour, 38 east north, because it goes east first and then goes north. So we can say it's 10 kilometers per hour, goes east first, 38 degrees north. So that would be the velocity. Now, acceleration, A, is the slope of the velocity versus time curve. So here, what's the slope of this line? It's a horizontal line. It's 0, no? Horizontal lines always have a
Mm-hmm.
slope of 0. So which means that acceleration versus time would look like this. We stop at 5 seconds, but the acceleration for this is actually 0 throughout. So that's what it looked like. Okay?
Mm-hmm.
And that's the idea. This is y equals 10x. The straight line has an equation of y equals 10x, the slope of which is 10, right? The derivative. So this is where it comes into play. If you have f of x as your distance versus time, then f prime of x will be velocity versus time, and f double prime of x, the second derivative from the distance function, is going to be a versus time, acceleration versus time. If your f of x is velocity versus time, then your f prime, if you take one derivative, if you go one level deeper, you have a versus time. You can't go any deeper than this. This is the lowest level. This is the highest level. There's nothing above this. And these three are related by their derivatives. We're going to do this later, not anytime soon. But as you can imagine, to come down, you take the derivative. There must be a way to reverse this, and there is. It's called the integral. So if you take the integral here, it'll give you the velocity function. And if you take the integral here, it'll give you the distance function. So that's the gist of this. And that's what this says as well. Well, S means position, so velocity is the derivative with respect to position. A is the derivative compared, so derivative of the velocity function. Or this symbol here means you take y double prime of the distance function. D squared s over dt squared means y double prime. F double prime of x, when your f of x is your s or your position function. So let's see this one. So this is your s function, your position function. I think a crucial skill would be to turn this. The question is asking us, describe the motion of this object. I think the best thing to do here, would be to just straight up sketch. I'm gonna align those boxes. See if you can align them. Right, like that. I'm gonna put it here. So I want to make like a precise sketch. Okay, those are aligned. Now we're gonna make a velocity versus time graph because that would allow us to explain the motion. It's gonna look weird, it's gonna look tricky, but it's not the end of the world. So again, we have 1, 2, 3, 4, 5, 6. Our goal is to graph a velocity versus time curve. How do you get velocity from a displacement graph? How are they related? It's a derivative, right?
Mm-hmm.
If you take the derivative of the top function, you'll get the bottom function. Derivative just means the slope. So step number 1, actually, because we don't have any like numbers, there's no y values given here, so there's no way we can come up with an equation for this. So we're not going to use the equation approach, we're going to use the graphical approach. The graphical approach just means that find the slopes and pinpoint those slopes at any point. So step number 1, this is what we're going to do. We're going to see where the slopes are 0. Is there any 0 slopes here?
At the top.
At the top, right? So at time is 2, the tangent is horizontal. That means the slope there is 0. Slope there is being 0 represents velocity. Means when the time is 0, our velocity is going to be 0. So we know we're going to come right here. Velocity 0, velocity 1, 2, like that. But we don't have concrete numbers, that's why. The only concrete number that we do have is slope being 0, and we're going to use that. We're going to abuse that. Anywhere else the slope is 0?
When it curves at the bottom.
When it comes to at the bottom, time is 6 seconds. Now think about this. Is the speed going up or down here? Now, when I'm talking about speed, I'm talking about these tangents. Eventually, it will become 0. At certain time, at time 2, the speed, the slope, when I'm talking about the speed, the slope is 0. But what's happening between 1, 1.5, 1.99? What's happening to the slope? We started here, right? Compare the slope of this tangent to this tangent to this tangent. What's the general pattern? Before it becomes 0, is the slope increasing or is it decreasing?
Increasing.
Slope is actually decreasing. If you think about it, it's becoming more horizontal. Yeah? Here is 0, right? Here it
Mm-hmm.
looks like it's 0.5. Here it could be 0.75. Over here, it's infinity because it's perfectly vertical. So what's happening to the slope? Is it increasing or decreasing?
Decreasing.
Slope is decreasing towards 0. What is it initially? It's vertical. What is it initially? It's almost vertical. It's infinity. Okay? It's technically not
Mm-hmm.
infinity because it's not vertical, but it's almost vertical, which means it's a large number. It's some large y value. So we don't know what the y value is. We don't really care. What we care is that it's decreasing. So this is what it would look like. We don't know what the y value is. So on the velocity, I have no idea what the y value is, but I do know that the slope decreases, decreases, decreases until at time 0, until at time 2, sorry, the velocity or the slope becomes exactly 0. Now think about what's happening after time 2 seconds, between 2 and 6. At 6, it's still right back to 0, right?
Mm-hmm.
Maybe we need a break point. Let's break it right here at 4. So here the slope was 0. At time 2, the slope was 0. At time 4, it looks like this. Did it increase or decrease the slope from here to here? Over here it was 0.
Increase.
It increased. It increased in a positive direction or a negative direction? Is a tangent positive or negative? Over here it was positive because it was going this way, right? Like a straight line, y equals mx plus b. If the tangent is going this way, northeast, then it's gonna be positive. If it's going southeast, like this one, the
It's
tangent
negative.
it's negative. So what we have so far is that from time 2 to time 4, the slope increased, but in a negative direction. Yeah?
Mm-hmm.
So we're gonna come right here. The slope is in right now, the slope is 0, the velocity is 0, but between 2 to 4, the slope is increasing. It's in the negative direction. That's why now we're underneath the x-axis. What about between 4 to 6? Is the slope increasing or decreasing?
Decreasing.
So over here, the slope is 0. Yeah?
Mm-hmm.
So it's come to a stop. So the slope is decreasing. The slope is decreasing, which means it's slowing down. It's going towards the origin. Decreasing means going towards the origin, going towards the x-axis here. So we know from 4 to 6, the slope is going to be 0. So it's going to slow down, slow down, slow down until it's exactly 0. Like that. What about between 6 to 7? What's happening to the slope? Increasing or decreasing?
Increasing.
Increasing. So it's increasing in a positive direction. So it'll look like that. And there we go. That's going to be your velocity time graph. And you can also turn this into an acceleration time graph by just finding the slopes. And all of these are straight lines. Let's say this slope is -4. I'm just going to assume, I don't know the height, but I'm going to assume that this is -4. So your acceleration will be -4 from 0 to 6 seconds. And from, 0 to 4 seconds, not 6, 0 to 4 seconds, the slope is -4. And let's say from 4 to 6, the slope is +4. And that's going to be your A to T graph. You're allowed to like teleport. You must be wondering how we go in from here to here. You're allowed to teleport when it comes to acceleration. Go from here to here. The way we connect them is like these dotted lines like that. That's how you can get the velocity and the acceleration graphs from the distance graphs. And that's how you can describe the motion as well. Like if I were to describe this motion, I'm going to be strictly looking at the velocity graph. For the first 2 seconds, the velocity decreased until it completely stopped. Between 2 to 4 seconds, the velocity increased in a negative direction. From 4 to 6 seconds, the velocity again, it decreases, slowed down, and it was not moving at 6 seconds. When V0, it stopped. Okay? When velocity is
Mm-hmm.
0, the individual, whatever, they have completely stopped. And from 6 to 7, again, the velocity increased. So that's how you describe these motions. Not. All right, let's talk about this. This is a question actually we have done before. I remember this distinctly. It'll be good practice. Describe the motion. So whenever it says describe the motion, it's probably asking you to think of it in terms of the velocity, from a velocity perspective. So always graph it. What kind of function do we have? What's st? How would you describe this function? T squared minus 10t. How would you describe this? It's a quadratic. You agree with that?
Mm-hmm.
Is it opening up or down?
Down.
So you want to look at the a value. So you want to look at this. It's opening up not down, because the 1 is the coefficient of t squared. Cool?
Mm-hmm.
What made you think it was opening down? Because the minus 10t. So you always want to look at the coefficient of the highest degree term, right? Like sometimes they will trick you. Look at this. 4x squared plus 3x cubed minus x4. Is this opening up or down?
Up.
So again, you got tricked there. You want to look at the coefficient of the highest degree term. So here it's -1, so it'll look like this. Yeah, you agree?
Mm-hmm.
This up means this way. The coefficient needs to be positive. This question is opening up, but that last example was opening down. So anyways, let's try and graph it. T squared minus 10t, it's a quadratic. What are the x-intercepts? It has two x-intercepts. We need to factor this to see the x-intercepts. Is there anything we can pull out? And this is not a man question. Man and quadratic formulas are strictly for quadratic trinomials. You need 3 terms in the quadratic. This is a quadratic binomial. It's not a man question. So factor this if possible.
You can pull out a t.
If you pull out a t, what are you left with?
T minus 10.
Yes. So what are your two x-intercepts?
0 and 10.
0 and 10. Where's the vertex? What's the x value of the vertex?
It's 5.
It's 5. So we have here, we have here. We know it's opening up. The x value is 5. How do we find the y value of the vertex now that we know the x value? You plug it back in, okay? You just find s
Mm-hmm.
of 5. You find s of 5. So that'll be 25 minus 50. It's going to be -25, right? Yeah, -25. So the scale is going to look super weird, but I'm going to say this is, maybe I'll just draw it upside down. So we just have a good picture. Why is the vertex -25? 5 squared minus 10 times 5. 25 minus, I don't understand why it's -25, but it doesn't matter. It's all good. It doesn't really change much. So our thing is actually going down, and we know it's at -25. So -5, -10, -15, -20, -25. So this is our vertex. Okay, it does make sense because this is opening up. I don't know why I thought it was opening down. So our curve looks something like this. We don't care about less than 0 because the range they've given us 0 to 12. So they've restricted the domain for us. At 12, it'll be 144 minus 120. At 12, the y value is 24. So if we wanted to, right there, the y value is 24. So there we go. That's our curve that we have. Now, what's the question actually asking us? Describe the motion of an object. Cool. So right now we have a displacement time graph or a distance time graph. It's probably displacement because they have the letter S. We need to turn this into a velocity time graph. And remember, we only know certain things. At time 5, what's the velocity? In other words, what's the slope of the tangent at time 5?
It's 0.
It's 0. So we know the object is going to come to a stop at time 5, yeah?
Mm-hmm.
Now think about this. Think about this. Before 5, from here to here, okay, is here to here. Is the slope increasing or decreasing?
Decreasing.
The slope is definitely decreasing. So initially, the slope was some high value. Negative slope or positive slope? Are the tangents negative or positive here? Like, would you say this is a negative or positive tangent? This shape? Because that's what it is.
Negative.
Negative. So the slope is decreasing, but it's coming from a negative direction. So the slopes to the left of 5 for this curve has negative slope, okay? It's decreasing, and that's our pattern. It has a negative slope, it's decreasing, and it's coming to a 0. So here, why don't you try it? Is it option A or is it option B?
It's B.
It's B, yes, because it's becoming 0 from a negative direction. So this will be the pathway. So the object decelerates, yeah,
Mm-hmm.
until 5 seconds. Decelerate means, and comes to a complete stop. Decelerate means slows down. Comes to a complete stop. So this is the motion. What about from 5 to 12? So it was horizontal. What's happening with the slope? Increasing or decreasing?
Increasing.
Increasing. So it'll look like this. And from there onwards, he's just traveling on this path at a certain speed. Now we can't really pinpoint what the slope is because it's a curve. Like the slope is going to change from here to here to here to here to here to here. The slope is going to change. So we don't know what the exact speed is. Let me rephrase that. We don't know what the exact IROC is, the instantaneous slope, but we do know what the average slope is. So the question could be something like this. Find the average speed or velocity for this entire trip. So it's asking us to find AROC. Remember how to find AROC? Right now we're dealing with tangent lines. What kind of lines do you deal with when you have average rate of change? Starts with the letter S. It's one of the reciprocal trig functions.
Secant.
Secant. So we're looking for the slope of the secant line. And whenever you're doing the average, you always start at wherever you start and go wherever you end. We don't care about the middle people at all. So now let's look at this. So the average. This point is 0, 0. That point is 12, 24. So the average speed looks like it's going to be rise over run. So 24 over 12, it's going to be 2 kilometers per hour. It's not kilometers per hour, it's meters per second. Meters per second. So that would be the answer if they're asking us for the average rate of change. Cool?
Mm-hmm.
Do you know how to go from kilometers per hour to meters per second?
Mm-hmm.
How? Here, we'll do some. It's okay. It's okay. So we're gonna call this dimension analysis. Dimension just means, it's just a fancy word. It just means the units, whatever units it has. So let's say we have a car. Let's use nice numbers, 100 kilometers per hour. This is your speed. How do you go to meters per second? Because the SI unit means a system international. The SI system, which is used by the global communication systems in science, is the SI system. Their length is measured in meters. Time is measured in seconds. What else can you think of? Mass is measured in kilograms. Can you think of anything else? That's what we're mostly interested in. Current is measured in amperes. Pressure is measured in pascals, yada yada. We're not concerned with these. We're concerned with length and time for this question. It's very important for you to be able to go from one unit to the other. And this is how you do it. This is how you should learn. Later on, you can come up with your own ways, and there's efficient ways, but this is the way to learn it. You don't want kilometers, you don't want hours, because the final thing doesn't have kilometers or hours. So you need to come up with a way to get rid of both of these one thing at a time. So I need to get rid of kilometers. The only way to get rid of that mathematically is to have a kilometer in the denominator. So I can cancel them out. Now I've introduced a kilometer in the denominator to cancel it out. And I want meter in the numerator, so I'm gonna do meter in the numerator. How many meters in 1 kilometer?
1,000.
1,000. So we're gonna multiply this by 1,000. Now this and this cancels out, right?
Mm-hmm.
Times. Now we got to do the same thing with hours. We don't want hours, so the only way to cancel that hour that's in the denominator is to introduce an hour in the numerator. We want seconds, so we're going to introduce seconds in the denominator. In 1 hour, how many seconds?
3,600.
3,600. So this cancels out with this. So the answer here will be 100 times 1,000 over 3,600. So let's see what that is. 100 times 1,000 divided by 3,600. That is going to be 27.78 meters per second. This is how you do it, okay? I know this is a shortcut. Just do this. You divide by 3.6, it'll take you to meters per second. To go backwards from meters per second to kilometers per hour, you'll multiply it by 3.6. But you need to know how to do it this way because not everything is going to be easy as meters and kilometers and hours. You might get something super weird. What can I think of? All right, yeah, torque. Torque is something weird. Torque units imperial. You know what torque is?
No.
So you don't have to know what it is. But it has a unit of, in the imperial system, in the American system, pound/feet. Now you need to know how to take this into the SI system, which is gonna be Newton meter, right? And this isn't as easy as last time. It's a lot more complicated. You might have to go from pounds to grams first, and then go into newtons. You might have to take some middle men to do this one. Last time it was straightforward. This one maybe is not as much. So I mentioned the word torque. Torque is denoted by this letter, tau. What it is this. It's only applicable in a circular environment. Torque is equals to force times the distance. This will be your distance. And how much force are you generating at that point? So that's what torque is. You'll probably learn more about this when you do grade, I don't know, 11 or 12. Probably I don't think you'll hear about it in grade 11. Maybe in 12 you'll hear about it, hopefully. If not, when you do grade 12 maths, calculus, it might come up there because it's a pretty popular metric of measurement. All right, here, let's do this another question, which is a quadratic question. Gonna cheat here because I have no intention of using the quadratic formula for this one. I think you are gonna need the quadratic formula to find the x-intercepts. Multiplies to -5, adds up to 30. Yep, nothing exists. So this is definitely a quadratic formula. So we're gonna graph this and we'll go from there. I'm gonna cheat for time purposes. All right, so I have the x-intercepts and the y-intercept. I just plotted it on Desmos, that's what I did. So boom, boom. So it has at negative 0.033, it has an x-intercept. The other one is at 6.0333, and it has a vertex at 346. So this is the sketch. Boom, boom, boom. We're talking about time and height. I don't know if we care about the ground, so we can ignore that axis. Time, we definitely don't care about the negative quadrant. So we're strictly looking at it at quadrant 1. All right, part A, determine the maximum height. I know we already have a plot here, yeah?
Mm-hmm.
But I'll tell you how to find the vertex. Vertex has two components, h and k. H will always be minus b over 2a. This is in the form of ax squared. This is in this form. What's b? B is 30.
30.
So here minus b would be minus 30. 2 times a, so 2 times negative 5. Negative 30 over negative 10 equals 3. But we already knew that. I'm just showing you how they found these. K, you just want to plug that value right back in. So if you plug 3 in here, you will get 46. So that's how they got it. So the maximum height, even if we didn't have this plot, we can use this method to find it. It's 46 meters. Determine the velocity of the ball when it is caught 1 meter above the ground. So it's probably caught not on the way up, right? Does it make sense that
Mm-hmm.
it's caught up on the way? That doesn't make any sense. So it's probably not there. We're looking at this right there. So it's caught right here. This is a position versus time curve. We're interested in the velocity. Know that velocity means the slope at that point. So we are looking for the slope, the tangent slope slope of the tangent line at y equals 1. All right, what's our approach for this problem? Do we know the x value when the y value is 1? We don't. Yeah?
Mm-hmm.
We know the y value. The y value here is 1, but what's the x value? Can't be 6.033. That's when the y value is 0. If you zoom in on it, it'll look like this. So this is 6.0333, but the 1 meter is somewhere here. And we're looking for this x-intercept, or the x value for this function when the y value is 1. So let's first find the x value. At what time is it caught? So we're trying to find at what time does he catch it. So y value is 1. We're going to plug it into our y value equation here. How do we solve this quadratic for t? It's a quadratic. You have to move everything to the same side of the equation. Step number 1. You want to move everything to the same side of the equation, okay?
Mm-hmm.
So 0, move this here, 1 minus 1, 0. Just remember, any polynomial greater than degree 2, equal to greater than degree 2, you want to move everything to the same side of the equation. From here, it's super simple. You pull out 5t, you'll see that it's going to be at 6 seconds. So t0, t6. So at time equals 6 seconds, so this is 6, he catches it. So we need to find the slope of the tangent when the x value is 6. How do we do that? We're given an equation. How do we find its slope at a certain x value? We find the derivative, okay? Remember, slope of the
Mm-hmm.
tangent means y prime. So the answer to this question is actually s prime of 6. So you first find s prime of t. Once you find it, you plug 6 in there, and that will give you the velocity of the ball. We can make a prediction. Is it going to be positive or negative, the velocity? Look at this tangent line. Will it have a positive slope or a negative slope?
Negative.
Negative. So let's find it. S prime of t would be the derivative of this, so that's negative 10t plus 30. S prime of 6 would be negative 10 times 6 plus 30, so it's negative 30. What's the unit of the slope here? And for that, you want to do rise over run. The unit of the rise over the unit of the run. What's the unit of the slope?
Meters over seconds.
Meters over seconds. And there we go, that's the answer. Negative 30 meters over seconds. So to find the velocity, when they give you a distance, take the derivative, plug in the x value. But this one, we had to find the x value. Sometimes they'll give it to you, but not here. Is this making sense?
Mm-hmm.
Yeah, this is just asking you if you can draw your tangent lines. That's literally what this is. So the velocity is 0 right here, right here, right here. Because it's perfectly horizontal, slope is 0, velocity is 0. When is it positive? Wherever your tangent lines are positive. So over here it's positive, 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 up until this point. So from here to here, it's positive. Same thing for this guy. From here to here, all the tangent lines you draw will be positive. Same thing from here to here. It's positive right here. And it's negative right here and right here. Yeah?
Mm-hmm.
That's it for this question. It's easy as that. That's all you have to do. So it's basically asking, can you draw tangent lines? Maybe we'll do this because we haven't done any cubics. All right, we have a cubic function there. Can we graph it? How do you graph a cubic function? You factor it. Well, that's the answer to any polynomial. You factor it. Can we factor this thing they've given us? So in our function, there's a bunch of t's, right? And we don't care about the negative time. So over here, can we pull out anything? What do you think?
A T.
A t, right? That's the only thing we can pull out. So let's pull it out. T, and then we get 1 over 3 t squared minus 2t plus 3 equals 0. And then you can use the quadratic formula for this. And that'll give you the two x-intercepts. You already know one of the x-intercept is 0. This will give you two more x-intercepts. The y-intercept is also 0. If the x-intercept is 0, the y-intercept is automatically 0, and vice versa. So we will know the three x-intercepts. The vertexes we won't know precisely, not yet anyways. Yeah, so cool. Maybe I will cheat. Yeah, I think that's the best way to do this. Because factoring cubics is not very fun. But this one is easy because you can just take a t out. All right, I have the sketch. Looks like it only has two x-intercepts actually. So this is our curve. Boom, boom, goes through here. We're not concerned about negative time. Comes here. There's a vertex at 1 seconds. The y value there is 4 over 3. Comes right back down to 3 seconds and then goes on forever and ever and ever. So there you go. That's the plot. Part A, determine the particle's velocity and acceleration at any time t. So what is it asking us in part A? They've given you a position function, right? They're
Mm-hmm.
asking you to find the velocity. How are they related? How do you get velocity from position? Think about it that way. Because part A is a 10-second answer. To find velocity, you just take the derivative of the position. That's it. So you just find s prime. So that'll be 3 over 3, 1. So t squared minus 4t plus 3. There you go. That's s prime. To find the acceleration, you take s double prime. You take the derivative of this. What'll that be?
2t minus 4.
2t minus 4. That's part A done. Part B. When does the motion of the particle change direction? Change direction means goes from positive velocity to negative velocity and vice versa. You're concerned about the velocity. So when does it change direction? So right now here, the slopes are tangent or positive. Over here, it's a 0, right?
And
So
then it
decrease,
changes.
and then it changes. So if you draw this out, it's starting off some positive y value, goes down to 0. So right there. From there, it increases until eventually, increases until at time 3, it jumps, it teleports to 0 again, right? So right here, it changes direction, right here, and right here. That's the answer to B. C, when does the particle return to its initial position? Initial position means where it started. So it started, what's the position value? What's the y value here?
It's 0
So the distance there, or the y value there is 0. When is the y value 0 again, is what C is asking you. At what time is the y value 0?
at 3.
At 3, there we go. So the answer is at 3 seconds for this one. So honestly, it's pretty easy, right? It just get a little bit difficult, especially if your distance function to begin with is weird. So if you have like a sine versus e to the x or something weird like that, then it's gonna be very, very difficult to graph it. But if you have a linear function quadratic, which is gonna be the case 99.9% of the time, they won't give you something that you can't sketch. Well, just for your curiosity, I'll show you this. So let's say our distance function is sine of 3x squared minus 8. So let's say that's our distance function. The derivative of this, our velocity function, will be cosine of that thing. And then you have to use a chain rule. So times 6x. So look at that. The purple one is the slope function for the green line. And the acceleration function would be the derivative of this, which would be this. So the derivative of cosine is negative sine. Actually, no, this one I have to use the product rule. It's not going to look like the black line there because I have to use a product rule. So let's just do it. So negative this times 6x plus cosine of 3x squared minus 8 times 6x. So this will be 36x squared. Looks super dumb, I know, but the green one is your position, the purple one is your velocity, and the black one is your acceleration. So what I'm saying is you'll never get something like this, but in real life, they could definitely exist. For our purposes, we'll always stick with linear and quadratic curves for distance. Okay?
Mhm.
All right, let's call it there for today.
Okay, thank you.
See ya.